So thank you very much for the very kind introduction, and thank you for the organizers for kindly inviting me and giving an opportunity to visit the Russian Academy of Sciences and meet you. And I want to follow up on the introductory remarks, which is, yes, I will try to convey some, say, development internals of SMT solving. It will be kept at a somewhat high level, at a mathematical level, but I hope it will give some inspiration, some idea of what are the main thoughts that have gone as a red thread through many of the little engines of proofs or the decision procedures or other proof engines that we have developed over the years as part of Z3. But it doesn't come in a vacuum. It comes from inspiration from coming to universities and conferences and meeting people who develop tools that use solvers. So I'm fortunate that I have several close colleagues where I work that develop tools. So I have that as a source of inspiration, but in the wider world, there's much more going on, and it keeps being an inspiration. So that leads to the aim of the talk. It's to I'll first describe a set of applications, and here I'll be mainly focused on the ones that I know more about. These are from Microsoft mainly, and then devote the second part of the talk to describe model-based techniques, so the so-called insights around developing solvers. So first, a primer of what am I talking about. So satisfiability model theories. It's about checking satisfiability of logical formulas modulo some background theory, where the theory may be integers or so arithmetic. And the solvers have specialized algorithms to deal with these theories. So here's an example, a one-on-one formula that belongs to this SMT. So it's a logical formula. It integrates the theory of arithmetic, you can see with blue here. And there's a theory of arrays, so applicative maps. And the rules for applicative maps is if you retrieve something that you stored in the same place, then you get the same back. And otherwise, you retrieve in the original map. And then there's an uninterpreted function thrown in for fun. So this formula is valid, and the solver is able to check for validity of this formula. So in particular, if you substitute x plus 2 for y, then you get a select at position x, which was just updated to 3. And then y minus x plus 1 is also 3, so f of 3 equals f of 3. So Z3 is an efficient SMT solver. What did we build it for? Well, the main thesis here is the program analysis tools ultimately rely on solving logical constraints. And Zohar Mana had the slogan that logic is really the calculus of computation. It's the means that we calculate around what computations may do. The aim of the SMT solver is then to lower the barrier of entry for program analysis tools to solve their logic queries. What is Z3? It's a general purpose theorem prover, and as the SMT solvers general characteristic, it has specialized algorithms for theories and then important workloads. And it's through interactions with users, I learned what are the important workloads. It's open source on GitHub, and there's a tutorial tomorrow where I will go through some of these pointers, but also an interactive use of Z3. So some of the current main uses of Z3 at Microsoft span a few different areas. So the Microsoft Security Risk Detection tool uses fuzzers and dynamic symbolic execution, and Z3 is an engine behind the dynamic symbolic execution. And here the idea is that you take program paths and it finds inputs that steer execution along certain program paths. In the networking space, I've been somewhat involved in tools around network verification, and we've developed two tools, or I've been involved with two tools in this space called Seguro and a FIB verifier, so a router verifier. And here the idea is to check firewalls and routing forwarding behaviors in data centers. In the Dynamics product configurator is a completely different use case. Here designers maintain a design space of parameters. So for example, you're a manufacturer of sofas, and you can have a choice between different fabrics and colors, and some combinations are feasible, others are not. And you can use logical constraints to specify the domain of what are the legal combinations of instantiating these parameters. And now what operators are interested in is if you fix certain parameters, which other parameters become fixed as a consequence. So essentially we use S3 as consequence finding. Project Everest has a grand goal of developing formally verified security protocols. So here the use of Z3 is to help in the verification conditions of program verification. There are several other uses inside of Z3, but these are, say, the ones I wanted to highlight here. So in the program verification space, we had a project around 2008 to 12, or I'm not quite sure of the dates, but these are approximated. In this case, we developed a verified C compiler aimed at verifying large fractions of the Microsoft hypervisor. The hypervisor runs the virtual machines and is super critical to the infrastructure also today in the cloud computing. As that project completed, another emerged, which is the Project Everest. And here the goal has been to verify very specific protocols that are important to internet activities. And in this process, a few derivatives have been developed. So one is called Evercrypt, and here it's a tool for a verified crypto library. So particularly develop say usable algorithms that you can plug into your cryptographic applications. And so for example, Firefox is using some derivatives of Evercrypt. Everparse is another derivative, and here the goal is to develop efficient and safe low-level parsers for network traffic. So it's notoriously difficult to get these parsers both efficient and correct if you write them by hand. So Everparse gives you a language for specifying legal packets using dependent types, and then derives efficient and verified parsers. So what you see here on the figure is the main flow of program verification. You take an annotated C program, run it through a VCC tool, then you get a procedural program that's in the Boogie language. Boogie gives you a verification condition generator, so from the low-level programs, it generates first-order formulas that are then establishing the verification conditions. So the other main use, and also in the wider community, dynamic symbolic execution has been incredibly impactful the past, I think, 15 years by now. And the idea is that you take a seed and run a random input to a program, and then run the program on that, extract which path was executed, and then from the executed path extract constraints, flip a branch condition or more to generate a new constraint that would guarantee a different path gets exercised. So here's an example of how that works. So for this a very simple program where you have inputs x and y, we could start with a seed where x and y are set to 0. That gives us an execution path, and probably this hash function is not going to hash 0 to 0. So we get into the error branch, or one of these two branches. And now the goal is to exercise the other branch, so to get sets to be equal to the hash of x. So the new constraint system will flip the branch that was taken, and then solve it. And in this case, it can find a solution where x is 0 again, but y is set to the hash of x. And in fact, we don't even need to know what's the implementation of the hash function. We can just plug in 0 for that value, and we would still get a constraint system that we can solve. So network verification here's applied in the context of taking the configurations that run in the routers and network devices and data centers. So what you see here is a figure of a schematic figure of more or less what a Azure data center looks like. So you have the servers on the bottom, and then you have 3 layers, or 2 or 3 layers of routers. And the goal is that these routers provide enough redundant paths between the servers for so-called east-west traffic, so within the data center, and also enough paths of north-west traffic, so in and out of the data center. And so, for example, if traffic goes within one pod of servers, then the expectation is that the traffic doesn't go beyond the blue routers. If traffic goes between pods, then the expectation is that the traffic doesn't hit the red routers, but only stay within the orange layer. And furthermore, doesn't take extraneous paths. So we have a tool that we call the FIB verifier, or RDCC. We extract the routing configurations, we pull them into an analysis tool that checks reachability invariance, and then when the invariants are violated, it flags errors. So before I delve into how that works, so the main point is we have these 2 uses of symbolic analysis in the networking space. So one is for access control, so connectivity restrictions, and the other was for forwarding. And what we have found is that there are several applications of using the formal analysis, both for validating designs of data centers and, say, refactoring firewalls, but also as part of the live operation of data centers. In the forwarding, when we check the forwarding logic, the base complexity of checking forwarding would be generate all pairs of paths. So that's at least cubic in the number of routers. So that gives us, so if we have tens of thousands of top-of-rack switches, then we'll end up with billions of pairs of paths. And furthermore, if we're like generating a path, how do we know that the path that we extracted from different routers corresponds to a consistent snapshot? So we bypass these problems by checking a global property of data centers by looking at what each router, the forwarding logic at each routing. And then we decompose the verification into local contracts. And in this way, we can parallelize and scale. So that was one of the, say important domain-specific insight for checking routing forwarding in data centers at scale. What we do specifically with the forwarding tables is we translate them to logic. So here's an example of a forwarding table. What it says is that there's an IP address range. So in the green text, you can see a range of IP addresses. Only the 28 first bits out of 32 bits of this address range are relevant. And then if the packet destination address matches this pattern, then it's forwarded to an alternative of 4 or 8 or 12 different next hops. So we can. So a forwarding table is essentially a big switch statement, and we can translate such switch statements into predicates. So we can define inductively a sequence of predicates that define the switch statement as if the current rule matches the packets, then go to the next hop, specify the rule, otherwise apply the next rule. And then contract checking ends up being a satisfiability check. So we either check that a contract, all behaviors of a contract are covered by the policy or the forwarding rules, or vice versa. When we're checking firewall policies, it's very similar. So here's an example of a firewall policy. So it has the allow and deny rules, and they also do matching on packet headers. And so these rules, preconditions, can be translated very straightforward into logic. Here I just give one example of the first rule. And then the combination of rules, and the typical approach of combining rules is to also, as a big if-then-else condition, that can also be translated. So now a firewall rule can be translated into a predicate by translating the big switch. Okay, so just two advertisements for some, a few other advertisements from other things. Imandra is a startup company doing analysis of financial service software, and they've developed a system around using OCaml programming language as input, and then do symbolic execution on the OCaml programs. Their domains are, they use algebraic data types and then use a 3 for ground arithmetic. Another application, this time from the quantum world, is on synthesizing quantum circuits. So this is a little advertisement for the tutorial. So the idea is that you start with pebbling the inputs, which are x1 to x4, and the goal is to move pebbles to the outputs y1 and y2 in such a way that you can only put a pebble on one of these round circles if all the children have already been pebbled. And then once you have pebbled the outputs, you're supposed to reverse the computation. So that makes the reversal of the computation makes the problem harder than register layout in traditional computers. So here's an example run through of a pebbling. So imagine that the pebbles in the sets here are applied to the circles on the left, and that gives a possible strategy for solving the pebble game. And now the goal of these is to find, first of all, a feasible pebbling, but also you may have resource constraints. You may have a constraint that says you can have at most 5 pebbles live at the same time, and in this case, this strategy would not be allowed. So, for example, P7 has 6 pebbles live. So we use bounded model checking for finding these pebble strategies. Another application is Axiomatic Economics. Casey Mulligan, economist, uses Mathematica, Redlock, and Set3 to solve to resolve his economic disputes with colleagues. So, in summary, we have developed analysis engines based on such applications. Here's a list of Microsoft Research logos for various applications over the years, and some of the main features that we have put into Set3. Okay, so that leads me to the second part of the talk, which is the technical session. So here we'll describe what we call model-based techniques in automated theorem proving. So the high-level idea is that in automated deduction, algorithms, there's end up being a combination of saturation and search. So you can view saturation as proof finding. So by saturation, I would say you, from one set of hypotheses, you derive some conclusions, and you keep deriving conclusions until you have derived your goal. So for example, if your goal is to derive contradiction, then you have found a proof by contradiction. The dual is to show that there's no contradiction, is to find a feasible assignment. And so these two aims may seem quite disjoint, but they can actually help each other. So in the process of finding feasible assignments, you may end up in a dead end. And in this case, the search engines do what we call conflict resolution. It's also known as conflict analysis, to derive new consequences, so build a proof. And this phenomenon is found in many places in algorithms. So for propositional SAT, a model finder, so the Davis-Putnam-Lohmann algorithm, originally developed in the 60s, is essentially a model finder. It does search, it does case splitting until it finds a feasible assignment. On the other hand, if you apply propositional resolution, it amounts to finding new consequences. And they were separated until the late 90s, in fact, these two methods. in SAT. And there are several good scenarios where saturation and search are valuable. So, for example, in Gaussian elimination and congruence closure, so deriving equality consequences, it amounts to pure consequence finding. It is saturation and it's efficient. And I would also say that there are successful instances of search in the case where you have search spaces that can be decomposed. So there's a method around parallelizing SAT search called cube and conquer, and the cubing part is essentially a search component. It decomposes search. And some instances of model finding is also quite successful. But for general purpose, conflict-driven cluster learning is much superior for finding certain proofs. So here, I'll just give one example of what I mean by this combination of search and model finding. So on the right, you'll see a contradictory set of clauses. There's no solution for P and Q that satisfies all four clauses, because the first clause says that either not P or not Q, and so on. What you see below is a resolution tree. So if you resolve the first two clauses with each other, you get not Q, and symmetrically on the right side. So search will go the other way of the resolution tree. You guess an assignment to Q, so set Q to true. And once we set Q to true, we'll propagate not P because of this clause. And that gives us a conflict with the next clause. Now, the conflict resolution method will resolve these two clauses and learn that Q has to be false. That gives us a back jump for the infeasible guess. And now we can propagate the learned unit, not Q. And then we get a conflict and we have reached contradiction. So that's search and saturation in a nutshell. But it translates to other domains. So for example, linear real arithmetic, Fourier-Marchkin can be seen as a saturation procedure. And simplex could be interpreted as a search method. So just to illustrate what I mean by search and saturation in the arithmetic case, let's take some inequalities. And the goal is to find values for A, B, C, and D, and E, and X that satisfies all the inequalities. And maybe A, B, C, D, E, maybe these letters are shorthands for more complicated arithmetic terms, but these are just the only occurrences of X, so we have isolated X. So what saturation could do is to say, well, if the lower bounds on X is A, B, and C, and the upper bounds are D and E, let's take the cross products of upper and lower bounds, and we'll have to satisfy all combinations of lower and with upper bounds. In contrast, what we could say, we start with a candidate assignment to D and E, and if the candidate assignment says D is 2 and E is 3, then D is a smaller upper bound than E. So we don't have to take a cross product between the upper bound E, because D is smaller. But that's just one case. Now, a different case would be that E is a smaller upper bound. But we can make these choices guided on a candidate assignment to D and E. Around 10 years ago, a number of methods emerged around developing search for linear real arithmetic based on these ideas. So I'll now describe embodiments of these ideas within SAT3, and it fits into the main architecture of the search engine. So in a nutshell, the main architecture comprises of a SAT engine and then engines for theories. So the SAT solver handles search, and the theory solvers handle this theory reasoning. And now, how do they integrate? They share what are the equalities, the theories. So each theory knows about the symbols that it can handle. So the theory of arithmetic knows about plus and minus, whereas the theory of arrays knows select and store. But they have to agree on which subterms are equal and which subterms are not equal. So that's the integration bus. And even in this integration, there's a way of using models. So each theory solver constructs a candidate model in isolation for the symbols it knows. And then each model in isolation implies some equalities on the set of terms in the formulas. So based on the candidate model that the solvers have, the goal is now to reconcile these candidate models into a big union, a big combined model, where they agree on all equalities. Now, if we can't have the theory solvers agree on equalities, we would backtrack and then continue search. So I'll just give an example of what this may look like. So suppose we have a solver that knows about the constraint x plus y plus z equals 1. And it can find a solution that says x and y to 0 and z to 1. A different solver knows something else. It knows that x plus y plus z is 2. And it will find a solution that x is 0 and y and z are 1. So the question is there a combined model for these two solvers? So in order to figure out whether there's a combined model, solver 2 will tell solver 1 that y equals z, and solver 1 will say that x equals y. And then in the end, they will search for a solution where x and y and z are all equal. And that's going to be infeasible in this case, and they will backtrack. So that was actually our first venture into using models for guiding search. And now for dealing with quantifier reasoning, it's quite powerful also to use models. So here I'll use a somewhat contrived example of what model-based quantifier instantiation does. So here we have a formula with a function f that maps integers to integers and two variables a and b that range over integers. And the question is whether there is a solution for f, a, and b such that the two assertions hold. And I've written them both in the SMT-lib input syntax that looks like Lisp, and then as well on the top of the right side. So we could start with a candidate model for the quantifier-free part of the problem. So we could set a to 0, b to 1, and then f maps 0 to 1, and otherwise it maps other values to true. So under that interpretation, we can plug in the interpretation in the quantifier and then see whether it's possible to satisfy the negation, whether there's a solution that satisfies that refutes, that is not a model of the for all quantifier. So we negate the model of the body of the for all quantifier, and then we insert the interpretation. So the interpretation will say, is it possible that if x is 0, then 1 else 2 is less than or equal to 1? Is that satisfiable? Yes, it's satisfiable if we set x to 0. And in particular set it to which is also the interpretation of a. So instead of setting x to 0, we set it to a, which is a more general solution. Then we instantiate the quantifier with a, and we have the contradiction easily. So how does this look like in a search procedure? Well, so we'll add the ground formula to a solver, then check whether the solver is satisfiable. If it's satisfiable, we get an interpretation. And then we have a secondary solver that checks the body of the universally quantified variable quantifier, but instantiated by the model. And if it's not possible to find a value for x that refutes the negation of the body, then in fact the entire formula is satisfied. Otherwise, we can find an instantiation from the model. So we also use models for decision procedures of arrays. This is, I guess, a little bit complicated slide, but the idea is that during search we will find candidate, will produce equalities between subterms, and based on which equalities between subterms we will create new, so if we have an equality between a subterm b and b prime, then an inference rule triggers. So the inference rule triggers if there's a subterm A that is a shorthand for store, and a subterm W, that's a shorthand for B prime of J. And furthermore, B equals B prime in the current candidate model. And then we will add this fact, because the candidate model can only satisfy the store select axioms if also this equality holds. So essentially we use the models to filter which inference rules get triggered to saturate with respect to the arrays of the axioms of the array theory. Polynomial constraints. So these are known as the existential theory of reals. So here's an example of two polynomials. So you have plus and times, variables and inequalities. So this is known as the Tarskian, or the existential version of the Tarskian theory of reals. And so it's decidable through cylindric algebraic decomposition. But CAD, also known as CAD, but CAD is a big hammer. It takes all inequalities and then generates all possible cylinders or possible subspaces of their, essentially their intersections. And what we do is, this is overreach for essentially establishing whether something is feasible. So here's an example where we can use a partial solution to guide search. So in this picture we'll have we'll focus on three inequalities. I'm sorry that they're not quite readable, but they represent the two blue lines above here and then the orange line. And then the question is whether there's elements in the intersection. And we can see from the figure that the green area is non-empty, but the point in search is to find this green area. So suppose we start with a candidate solution where we set x to 1/2. And then the question is, can we extend the value 1/2 of x to some y that's in the feasible region? No, you can see easily from the figure that there's no y that falls in the green feasible region. So what the pruning solution approach for NLSAT does is find an explanation for why x is a bad choice, and furthermore the explanation would be suitably strong to also rule out infinitely many bad choices. To generate an explanation for why x is a bad choice, it suffices to just use the two blue inequalities. The green inequality is not necessary to show that x1/2 is infeasible. All right, so, and one can even take these ideas further as a full integration method. So the model constructing SAT architecture for decision procedures considers assignments to variables during search. So arithmetical variables may be assigned to values, in this example, 0. And then you can also assign values to predicates. That gives us a trail of assignments. And then when we detect that the trail of assignment cannot be extended to a full feasible solution, we'll apply a conflict resolution and then generate an explanation for why that trail cannot be extended. So I want to conclude, more or less conclude with a newer instance of the integration of models and deduction in an application to arithmetic. So this is somewhat new work, but I think it's fun. So in this example, you'll have, we are solving linear arithmetic enriched with a so-called star operator. So I'll try to explain what the star operator does. On the left side, we have two polyhedras, F2 and F1. F2 is a small closed polygon, and F1 is half open. And we can see that the intersection of these two polyhedra is empty. So there's no solution that satisfies the conjunction of F1 and F2. On the other hand, we can take a so-called star operator over F2. And what star means is that if you have a, x comma y satisfies F2 star, if there's a linear combination of solutions to F2 that add up to x and y. So in other words, there's some x1 to xk and y1 to yk, such that f of x1, y1 holds, f of x2, y2 holds, and so on. And then they add up to x and y. So in this figure, the blue points are the members of F2 star. And you can see that there are lots of points, blue points, that belong to F1. So the conjunction of F1 and F2 star is satisfiable. Okay? Clear? Question? All right, so, so we can express the star of F2 in linear integer arithmetic. So the proof of this claim is sketched as follows. So, so every Pressburger formula, or linear integer arithmetic formula, can be expressed as a union of semilinear sets. So what's a semilinear set? It's a point, A, and a set of basis vectors such that every solution, every combination of basis vectors plus that point. Yes? Question? Okay, so such that every solution to the basis vectors plus the point is a member of that semilinear set. So every linear arithmetic formula, no matter what conjunctions, disjunctions, and so on, can be expressed as a union of such sets. Okay, so suppose that we have such a representation, then we can express the star operator as taking, points from any of those semilinear sets, add them up, but just require that if we can only use the basis vectors if we have also chosen the point, the A, the offset A. So this we can express with the implication, and now we have a formula that, also a arithmetic formula that specifies F2 star. So the brute force solver expresses F2 star using semilinear sets and then uses a linear integer arithmetic solver. So the catch is that this is completely impractical. So here's a better approach to solving these. So the approach is, the strategy is to simultaneously generate an under and over approximation of F2 star. And then we'll finish whenever the under approximation together with F1 is set, or the over approximation together with F1 is unset. And whoever finishes first wins, right? It gives the answer. And then we're going to terminate because in the end we can generate an under approximation that is the semilinear sets, and that is a finite object. So we'll be guaranteed to terminate. But we could terminate much quicker when either of these two termination conditions are satisfied. So how do we generate the under approximation? Well, 0 is a member of every under approximation to use. So 0 is a member of F2 star. And then we're going to maintain an under approximation of semilinear sets to F2. And given an under approximation of semilinear sets, then we can also under approximate the star. And then we can check whether, first of all, we have finished. Or we can also generate new points that are not covered yet in the under approximation by solving a formula of this form. We can find an x and y that satisfies F2 as a member of F2, but not which is not in a U star. And then we can keep adding vectors and reduce them. So that's the building an under approximation. So in one disguise, this is model finding. We find a possible model XY, and we extend this under approximation. Over approximation can be sketched as follows. So from the so our initial under approximation may be given by whatever is our current under approximation, and then we can build weaker under approximations by adding solutions to F2. We can also go backwards from F1. In the initial backwards approximation of F1 is B0, and then we can add points that where F2 vectors can reach B0. And if the over approximation so if F2 star is really unset with F1, then these two regions will never meet each other. So in the process, so for every unfolding of these under approximation on their backwards region, there will be separated point. So we can find interpolants, and in this case, they're illustrated as if they're half planes. And those half planes can be added up until they are inductive over the overapproximation. And that gives us a way of terminating quicker. So that was, say an illustration of using under and overapproximation. We didn't leverage the duality fully between the model search and deduction. Here we used the under approximation to strengthen the over approximation, but not in the other direction. So there are more things we could do in this space. Okay, so we also have methods for solving quantifiers. I will not go over this, but just end up with a summary. So, I claim that SMT solvers have come into quite widespread use in the past decade, and that's thanks to a large span of applications and technical advances. I gave some examples of application and what I believe are a good set of techniques to drive technical advances. I also think it remains a trove of future opportunities to drive automated deduction technologies. But the model-based techniques are not the only ones that could drive automated deduction. So in particular, there's quite interesting developments these days in so-called cubing. And that's, in a nutshell, a way of establishing a problem decomposition. Another set of developments is in devising so-called strategies. And so a strategy is, in my definition, a way of pruning search space between from a part of the search space that would produce solutions as long as another search space would do. So you wouldn't lose the existence of solutions. You might lose specific solutions, but you wouldn't lose existence of solutions. Okay, so that is the end of my talk. So thank you very much.
Thank you. Вопросы? Questions? We have 2 microphones over here, so I will give you a microphone if you just raise your hand.
Thanks a lot for your talk. It is another area for me, but I have a practical question. In the first part of the talk, you mentioned that solvers help to find $1 million bugs in the software.
Yes.
And I wanted to ask, is it really, do they really give better knowledge than experts, or they really help to make it automatically? What is?
Yeah, so the $1 million slogan is from the symbolic execution, and so $1 million is the cost of fixing and deploying a security vulnerability for Windows, and there the bugs are found in low-level, essentially code that parses files, JPEG or similar things, PDF. So code that gets embedded in browsers and essentially part of an attack surface. So so they're not found by manual inspection. So they're found by these fuzzing and symbolic execution tools.
So it helps to find the input which can reach the error in the code?
Yeah, yes, that's correct. Yes.
And it is something different from the fuzzing technique, right? When you get the input.
So we could call it white box fuzzing, in the sense that you have access to the instructions that are executed. I mean, the real picture today is that the tools use hybrid techniques of so-called black box and then this following the instruction sequence.
And how do you see the future of this technology? Can it become even more deep and successful in finding bugs?
Yeah, I think one development is at which layer do you embed this technology? Do you have access to the assembly and then the execution trace? So if you can embed it with a good, instruction tracer at a the lower level you can do the instruction tracer, the better you have a chance of integrating this technology. So that has been a big part of developing these tools. They have always depended on instruction tracer.
Thank you.
Hi, thank you for the talk. And I have a question. Maybe you know if there are any applications of Z3 to solving relational algebra problems. And I'm mostly interested in graph problems.
Yeah, so there have been some developments over the years on relational algebra. I have in some special cases one can do it with what's built in, and in other cases people have developed encodings, embeddings. So related to relational algebra, maybe say transitive closure have actually a feature that gives you a transitive closure of a ground relation, and so that's for ground formulas that's decidable but not expressible in first order. But we can do that as a decision procedure.
Okay. Anybody else?
Thank you for your talk. I have one question. I know that Z3 support parallel solving.
Sorry?
I know that Z3 support parallel solving. Is it more effective? In what cases is it more effective to run Z3 in Z-mod, or to run many instances of Z3 to try solve different problems? There's in this Z3 release there's an out-of-in-the-box parallel mode for the SAT solver. It's not heavily tested. What I have tested is a version in Azure where I've distributed solving over a few hundred cores. And there, what I found was that this cube and conquer approach is much more effective in finding solutions to hard problems than the so-called portfolio approach, where you run multiple instances on the same problem but with different seeds. So an order of magnitude better to do the decomposition and the running. How it is more effective to run parallel solving to solve one path constraint, for example? Or if I have many path constraints, it's better to run multiple instances and each Z3 instance. Oh, okay, sure. So for multiple path constraints, sure. Yeah. But again, you're doing a problem decomposition by running on multiple. So you're taking, say, maybe a set of path constraints that are encoded as a formula versus multiple simpler path constraints that are that are basically instances of the more general path constraint. And that I would claim is an instance of cubing. So there you will have done the decomposition up front and then run the solvers on those instances, and that is more effective. Thank you.
Thank you very much for a very interesting talk. As far as I know, Z3 functionality for interpolation is not developed anymore in active state.
That's correct. Yeah. So I took it out a couple of years ago because it wasn't active. There's an indirect way of getting interpolants for arithmetic using the Horn clauses. So we can specify so we use this in the Lia star. We set up an interpolation problem here as Horn clauses. So I is an uninterpreted predicate, and we can write down these two formulas for all x0, for all x1, etc. And this formula is going to be satisfiable, and then the satisfying assignment to I is an interpolant. So the spacer engine finds these interpolants for pure arithmetic. For a combination of arithmetic and uninterpreted formulas, we're currently working on a model-based technique for the interpolants.
So we can expect that this functionality will be available sometime.
If we're successful in proving the theorems that we would like to prove, yes.
Good, thank you.
Okay, so I will use the privilege of being a moderator to ask the last question. I'm sorry. From my point of view, from the program license point of view, my interest mostly lies in the quantified formals, which I actually have skipped, but my question is more of a general idea. So we and verification people and other people in our community use solvers, as I said, mostly as a black box. And sometimes we find out that the solver doesn't behave as we expect. So either it takes too long to solve some queries or something like that. How can we first debug something like this on our level of not going too deep into the solver internals, and how do we better interact with the community, for example, to pass our queries to make for you interest in the task of improving solvers for our use case? So this is some kind of a more general question.
All right, so I'd say the SMT Lib initiative by Clark Barrett and Cesare Tinelli and others, I think have been a real good driver. And so I always encourage people to submit benchmarks. So this is both gives a community drive and also a way of getting feedback on these examples. In part of debugging why something doesn't work, generally it's an open-ended thing, but we have some tools for profiling instantiations, and that's the first thing I point to. So we have profiling tools for what the solver does, and that's a first step.
Then let's thank again the speaker. Thank you, Nikolaj.